Hello, everyone. Welcome back. Today, we're talking about probability distributions and explain what they are and how we use them. So, our goal, as it says, we understand the basic concepts of probability distributions, be able to find the mean and standard deviation of a probability distribution, and then be able to use these distributions to find probabilities. So, first, let's explain what a probability distribution is. So I'll read this as it says. A probability distribution is a description that gives a probability for each value of the random variable. We'll explain what a random variable here is in just a moment. This probability distribution is often expressed in the format of a table, which we'll see today, a formula, or a graph. A random variable, x, probably is written as p of x, like a function. Probability distribution has the following requirements. So this random variable x, for example, if we're talking about the probability distribution of flipping a coin, then x would be either getting a head or a tail. And so then for each x, either head or tail, then p of x, you get the probability of that happening. Or if we think about rolling dice, rolling one six-sided fair die, as we'll see in a moment, then your x, your random variable, are the numbers 1 through 6, the faces you can get. And then for each face, you have the probability of getting that face, that number. So there's a numerical random variable, x, and its number values are associated with corresponding probabilities. That for each possible, the thing about the x essentially being your sample space, everything can possibly happen. And for each one of those numbers, there's a probability of getting that number. The sum of all the probabilities must be 1, and this Greek letter sigma means sum, and so the sum of all the probabilities have to sum to 1. So remember, the probability of a certain event is 1. So this is essentially saying the probability of getting one of those outcomes, it don't care which one, is 1. And basically add up all the probabilities. It's saying the probability of one outcome or the other till the end. Now, small rounding errors are acceptable. Sometimes in using decimals, you may not always get exactly 1 at the very end. And then for each probability has between 0 and 1, including possibly 0 or 1, as we've seen before, the probabilities. Now, random variable, typically represented by the variable x, has a single numerical value determined by chance for each outcome of the procedure. By here, random, we don't necessarily mean haphazard. It doesn't necessarily mean it can be anything. It's like in the case of rolling dice, rolling one fair die. The only possibilities are the numbers 1 through 6, but we don't know which one of it's going to be. But we have a probability telling us what we expect to get each one for each face. But still, that's what it means by random. Doesn't mean anything can happen, but just of the outcomes that are available, we're not sure which one we can get, but we'll have a probability of that. And there are two basic types of random variables: a discrete random variable, where we have specific collections of outcomes that's possible, or a continuous random variable, where you essentially have intervals of numbers which are possible. For example, once again, like flipping a coin, rolling dice, those are discrete random variables since you only have certain possible outcomes. But if I said, what's the probability that, any random man picked in the population is between 5 feet 5 inches tall and 6 inches tall, there's an infinite variety of possible heights between those two values. That would be a continuous random variable. Now, a probability distribution also has a mean and a standard deviation. And the mean is called the expected value, which isn't always the best name for it. But let's explain what it is first. So the expected value of a discrete random variable x is denoted by the capital letter E. It's the mean value of the outcome. So in terms of population, E is the same as mu. And E can also be found with this formula, once again, this sum, multiplying each random variable, each possible outcome, by its probability, then summing up all those. We'll see that later. And then we have what's called the range rule of thumb, where if once again, using the standard deviation, which you also can find of a probability distribution, that if what this essentially says is if our outcome is greater than 2 standard deviations or more above or below the mean, that's there to be a rare event. And typically that turns out to be, as we'll see in the next paragraph, talking about the rare event rule for statistics, that typically what these both say together is that if the probability of something happening is basically less than or equal to 0.05 or about 5%, it's rare. Whether that's a number of successes or a number of failures, and usually low number of successes or usually low number of failures, and the probability of each of those is 5% or less, and those are considered to be rare. Now, finally, we're looking at an example. We have the standard deviation is calculated by this formula. So it's not the same as similar concepts, not the same as the mean. We have to use the mean, which is mu. Then it's found by this time summing up the random variable squared times the probability of each of x, and then subtracting mu squared, then taking the square root of that. Now, also one more thing to say about this mean or expected value. Sometimes expected value might be kind of misleading. It doesn't mean, expected value does not mean the value we expect to get in a single experiment or single trial. It's like flipping a coin. Flipping a coin or rolling dice. If we're rolling a fair die, we expect to get each one of those. If it's a fair die, we expect to get each one of the 6 numbers equally. But as we'll see, the mean is something else. The mean is kind of like a balance point for the values. And this is important in many areas of where probability is actually used. For example, in a casino game, remember, casinos are businesses and their goal is to make money. So they're, in terms of the point of view of the player, these games have negative expected values, meaning that they're balanced negatively, where you're more likely, or if you play the game many, many times, or more realistically, many people play the game, although there will be big payoffs every now and then over time, it's balanced toward the negative, so that over time, people will be paying more into it than they take out of it. And it's also true with insurance and other things use probabilities. So now let's take a look at some examples. First probability distribution we want to do is for rolling a single fair die. So remember, this is going to be a 6-sided die, okay? And each side is equally likely. So there's 6, our sample space, or possible outcomes, are numbers 1 through 6. So in this case, we'll make a table to create our probability distribution. So we're on this side, we'll put x for each one of the 6 sides we can get, and then for each one of those, the probability of that side. So we have, of course, the sides 1, 2, 3, 4, 5, and 6. And then the probability of each is 1/6, 1 out of 6. Now, as a decimal, then that's approximately 0.17 for each one. And since this is a fair die, each side is equally likely. Now, if it wasn't a fair die, then these would be different. Okay, so this then is our probability distribution. So for each possible outcome of the numbers 1 through 6, and this is a discrete probability distribution, then it lists for each random variable, each possible outcome, it lists the probability. Okay, this tells you then, this is in kind of in a table form, then what we expect. Now, the next question is, does this fulfill the requirements of a probability distribution? So let's go back and take a look what those requirements were. So, numerical random value x, this number of values are associated with corresponding probabilities. We see that's true. Then the others is the sum of the probabilities must be equal to 1. So if we calculate the sum of the probabilities, if we sum up p of x, and what that's going to be is if we add all these up, okay, and since this case they're all equally likely, there's 6 values, so 6 times 0.17. And if you do that, then you'll see that it doesn't come out to be exactly 1. In fact, it comes out to be 1.02. Okay, but this is okay because that's due to rounding error. That's because actually 1 divided by 6 is basically 0.666 repeating, so we had to round off. And so it's not going to be exactly 1, but that's close. And that's also what we said here. Small rounding errors are acceptable. Of course, you want to make those rounding errors as small as possible. And the other question was, is for each probability in the table, each p of x, we want to make sure the probability is between 0 and 1. And we see that's also fulfilled, because each one is 0.17. So, of course, that's true of any probability. Probabilities always have to be between 0 and 1, possibly including both 0 and 1. Now, I want to find the mean and expected value of this. So the mean, E, which is equal to mu, is basically found by summing up x times the probability of x. So essentially it's a weighted average. And what this means then is we take like a 1 times 0.17 plus 2 times 0.17, and then the dot means we continue all this way all the way up to 6 times 0.17. Okay, now we're going to switch over. There's made a Excel spreadsheet to help us with that, and also help us find the standard deviation. This column, that's what we have right here, x times p of x. So it equals, and then we're going to make this times that cell times this cell, then highlight that and click on this little box at the very bottom, drag this down, that fills in that with all those values. Okay, now what we want to do then is sum that. So our mean, or the expected value, is equal to the sum. So just start to type in the word sum, double click on that, and then we can drag these values here. And we find out that comes out to be approximately 3.17. And once again, that's also partial rounding error, 3.57. So actually, this is a bit of rounding error. So it should be actually 3.5. Now, why is that? Well, I said the mean or expected value is essentially a balancing point. Okay, so if you think about this, there are these 6 possible values, all have the same probabilities. And so if we're thinking about balancing that, essentially it's like a uniform distribution, all the same value. Our balance should be right in the middle, which is right between, halfway between 3 and 4, or 3.5. Okay. So that's our expected value. Once again, the balance point. Now, let's find the standard deviation. So sigma is this formula. Let's go back and take a quick look at that formula again. The different calculations are the square root of another sum, but this time of x, not x, but x squared times p of x. Then from that, we subtract the mean squared. Okay. Now, I'm also on our Excel spreadsheet, and also make the spreadsheet available in the notes. We have that. So what we're going to do here is an equal. So this cell squared, then times this cell, hit enter. Then once again, click on this corner and drag that down to fill in the rest of the values. Okay. Now, once again, we want to sum that. Now, a couple things we have to do. And so that's going to be the standard deviations, abbreviated. So, you know, this is the square root, or I'll do this as call the square is the same as the 1/2 power. So this is going to be basically this, I actually need to do a sum first. So let me sum this column. So give me just a moment. Let me change that. This is equal to, once again, SUM. Double click on sum. Then highlight all of these and then close the parenthesis. Okay, that's the sum. Now, our standard deviation is the square root, and the same as the 1/2 power. This value, let me do it equals, sorry. This value minus this value, the mean squared, and then raise that to the 1/2 power, or the 0.5 power. Okay, so remember, it's going to be this sum minus the mean squared at the 1/2 power, and that turns out to be about 1.65. So I can fill in those details. So this was, double check, this number here was about 15.47 minus, and then this was 3.57 squared, and this came out to be about approximately 1.65. Now, the standard deviation kind of has the same meaning here as it did as you've seen standard deviations before. So this is on average, this is how far a typical value deviates from the mean. Now, let's look at another example to get a better feel for this. This time we'll look at one where all our probabilities are not the same. And so that will give us kind of a better feel of what often most happens in real life. Let's look at this example. This is below is a probability distribution where X represents the number of yellow Labradors in a litter of 7 Labrador puppies. So be familiar with labs. They can be black, they can be yellow, they can be kind of chocolate colored. And so basically, out of 7 Labrador puppies, how many of them are going to be yellow? So it's possible 0, none could be yellow, 1 could be yellow, all the way up to maybe all 7 could be yellow. So what this probability distribution shows is for each of those possibilities from 0 to 7, it gives, based on this history of yellow labs, a breeding history of 2 champion Labradors, it gives basically the probability of that many yellow labs out of all the yellow labs in that particular litter, out of up to 7. Okay, out of 7 Labrador puppies, a litter of 7. So this is our probability distribution. So it tells us for each one of those possibilities and what the probability of that happening is. And also, if you add this up, and we'll also look at this in Excel, you should get 1. We'll see that in a moment. In fact, maybe we should go ahead and take a look at that now. So actually, let's take a look at this. On my second sheet, we have this. That's our probability distribution. So if I sum that, double click on sum. It's going to maybe some small rounding errors, but this should be 1, exactly as it should be. That tells us then this is a valid probability distribution. Now, what's the probability of having 0 yellow lab puppies? So the probability, right, this probability of 0, we can get that directly from our table, probability distribution. Probability of 0 for x, random variable of x equals 0, plug it in like a function. Our value is 0.21, approximately 21%. So 21% of the time, we should expect to have no yellow labs out of this litter of 7 lab puppies. What's the probability of having more than 0 and up to 7 yellow lab puppies? Okay, so this time, the probability I put as x, the probability is x is greater than 0, okay, up to 7. Now, we could do is, so this is an or question, and these are all mutually exclusive since you can either have 0 or 1 or 2 or so forth. It can't be any overlap. So this, you could do this as a probability of 1, not including 0, plus the probability of 2 plus ... all the way up to the probability of 7. And that's valid. But there's an easier way to do it. You can use the idea of a complement. So the probability of x is greater than 0, since this would be mutually exclusive. So you're either going to get 0 or greater than 0 yellow labs. And so you can write this as 1 minus the probability of 0. That's a much easier way to do it. So 1 minus 0.21 is going to be 0.79. So that's 79% chance, approximately, of getting more than 0 yellow lab puppies in this litter of 7. And once again, this might be, you can do this on your own. If you add up all those other probabilities, you get the same thing, 0.79. Okay, next. What's the probability of having 4 or 5 yellow lab puppies? So once again, let's take a look at what this means. So once again, this is an or question. So our general rule is to add each one. So probability of 4 plus the probability of 5 minus the overlap, probably of 4 and 5. In this case, there's no overlap. You can't have, and that's also why they're discrete to some extent, because you can't have, it's either going to be 4 or 5. There's no in between. There's no overlap. This becomes just a probability of 4 or 5. So if we look back at our table, probably getting 4 is 0.05. Probably getting 5 is 0.07. So we simply plug those in. And if we add those, it's going to be 0.12 or 12%. There's a 12% chance that we'll get either 4 or 5 Labrador puppies. I don't care which one it is, that's the probability. Next, what's the probability of having fewer than 4 yellow lab puppies? All right, this is probability that X. What does fewer mean? Fewer means less than that. We're not including 4. That thing will be X is less than 4. And so this way, we pretty much have to simply do it this way. So that's a probability of, so the numbers I could be happy with this way, you're getting 0, 1, 2, or 3 yellow labs. So it's going to be the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3. And if we look at our table and find those, it's going to be 0.21, 0.18, 0.33, and 0.07. 0.21 plus point, the next one was 0.1833 and 07. So that's 0.33 plus 0.07. And if we add these together, let's see what we get. And that turns out to be 0.79 or approximately 79%. So about 79% of the time we expect to have fewer than 6 labs, fewer than 4 lab puppies. Now let's look at number 5, which is similar. I have to decide if it's the same. What's the probability of having at most 4 yellow lab puppies? What does at most mean? Okay, well, at most, so think about what you're happy with and what you'll be willing to take. So that means you're anything less than 4 is fine, but also at most is 4 okay? Yeah, that's at most. Okay, so this means 4 or fewer we're happy with. So then the probability, in this case, we write it in a similar way. It's almost the same as this, except this time we consider 4 is okay as well. So this is going to be X is less than or equal to 4. Okay, and so this then is going to be probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3. So I'll give an extra line there plus the probability of 4. Okay, now we could add all these again, but we know this is 0.79. So all I have to do is add 0.79 to the probability of getting 4 in this case. The probability of getting 4, we've actually seen that before, is 0.05. And if we add those, that's going to be 0.84 or 84%. So there's an 84% chance of having at most 4 yellow lab puppies. Another way you can think of that as a complement of having 5, 6, or 7. Another way to look at it as well. Okay, now find the mean and standard deviation of this probability distribution. So the mean is the expected value. So once again, it's going to be the sum of X times the probability of X for each one. Okay, once again, I'm not going to do an Excel spreadsheet to help us with that, so I'd have to do it by hand. It's the same way it was before. So the mean, or once again, it's the expected value. Well, first I'm going to do this. So this is going to be equal to X, that box, times that entry. Then click on a little square, click on the corner, drag down and fill in all of those. And the mean is just going to be the sum of those. So we're going to do sum, double click on sum, and then click on here, include all the values, close your parentheses, and then enter. That gives our mean of 2.17. So that's our balance point, 2.17. Okay, so if we look back at our table, that's our balance point. So that means that most likely you're going to get something on the low end. Okay, so if it's kind of balanced about 2.17, right about here. Okay, if you look at our probabilities, that kind of makes sense. The bulk of them are down here. So expect in most cases to get it's balanced this way. So expect in most cases get a lower number of um, yellow lab puppies, either 0, 1, or 2, than some of the higher numbers, kind of balanced this way. So this is definitely not like the other one. It's not uniformly distributed. So it's not halfway, it's not in the middle. It's kind of balanced right about here. And then the standard deviation. So once again, that's going to be the sum of x squared times p of x for each value, then minus the mean squared, as we just saw. So once again, we'll do this on Excel. So we need to fill in this column. So we're going to square. So we're going to take the x value. Oops, first I have to do an equals. Then the x value, raise that to the second power, then multiply that by the value in this column, then hit enter. And then once again, click down and do the same for each one of those. Okay. And so the standard deviation, we also need to do a sum. Let's go do a sum of that column as well. That will just make it a little bit easier. So a sum of this column. So click SUM, double click on that. Then once again, drag those and close your parentheses. So that sum is that. So our standard deviation is going to be equals to, so I'm also going to do this as a raises to the 0.5 power, is the same as the square root. So this is going to be that sum minus the mean squared, those are parentheses, then raise this to the 0.5. Okay, so once again, it's that sum of that column minus the mean squared. And the whole thing is raised to the 0.5 power, and that's going to be approximately 1.90. If we round it 2 decimal places, about 1.90. Okay, so once again, standard deviation the same way tells us that on average, we expect each value that we get to deviate about 2 from that. Okay, last question. Is having 7 yellow puppies an unusual value based on the range rule of thumb? Is this a rare event? So first off, let's find the probability of 7. So go back to our probability distribution. 7 is 0.03, or about 3%. And kind of intellectually, we think that's probably unlikely to get all yellow labs. Okay, now based on the range rule of thumb, let's go back and take a look at this. The range rule of thumb says that basically, if it's 2 standard deviations from the mean or beyond, either positive or negative direction, then that's a rare event. So this is so 7. Now here we're thinking about is our mean. Okay, so 2 standard deviations above the mean. So 2 standard deviations above the mean. Okay, 7. And that's going to be our mean, which is once again about 2.17, plus our standard deviation of 2 times 1.9. Each standard deviation is 1 above, so this will be 2 times 1.9. Let's see what we get there. Okay, all right, so this comes out to be 5.97. Okay, so 7, what this says then, so 7 is greater than 2 standard deviations above the mean. So this is an unusual value. based on this range rule of thumb because it's 2 standard deviations above the mean. Okay. Now, is this a rare event? And this also is a rare event. Since the probability of 7, which is 0.03, said for a rare event, that's what these next paragraphs here said, basically the probability is less than 0.5, it's sure to be rare. So the probability is 0.03, which of course is less than 0.05. So based on that is also a rare event. So based on both those things, this is an unusual value based on the range rule of thumb, and also is a rare event based on this idea of rare events where your probability is going to be less than 0.03. So what we've seen today is we learned how to learn what a probability distribution is, the basic concepts, how to find the mean and standard deviation, also how to find probabilities using the probability distribution. And this was a discrete probability distribution. And for future topics, we'll look at other discrete probability distributions, then also continuous probability distributions as well. Thank you. Have a good day.